Ayubuwan. A very warm welcome to all my dear students joining us today here on the Study Hub Sri Lanka channel. I am absolutely thrilled to have you with me. Today we're diving straight into a real masterclass on Unit 2 of your GCE A-level chemistry syllabus, structure and bonding. Now I know, this topic can sometimes feel a little bit overwhelming, right? But please don't you worry at all. We are going to break it all down together, step by step, using some really clear visuals so you can totally master this molecular architecture and just ace those past paper questions.
Okay, so here's our quick roadmap for today's explainer. We'll be covering VSEPR theory, our base geometries, lone pair distortions, hybridization and bonds, resonance and stability, and finally, polarity. We're covering all the bases.
Section 1, Introduction to VSEPR theory, or as I like to call it, the core directive.
So, this fundamental law is called VSEPR theory, valence shell electron pair repulsion. It's a bit of a mouthful, I know, but the actual core directive is incredibly simple. Think about it. Electrons are all negatively charged, right? So naturally, they repel each other. VSEPR theory basically just states that the electron pairs surrounding a central atom are going to arrange themselves in 3D space to get as far away from each other as humanly or chemically possible. They literally just want to maximize their distance to minimize those repulsive forces between them. It's exactly like a group of people trying to find their own personal space in a super crowded room.
But here is where it gets really interesting. You see, not all electron pairs take up the exact same amount of room. If you look at the visual inequality scale, you'll see a bonding pair interacting with another bonding pair. Now, because these electrons are stretched out tight between two nuclei, they actually take up less space, meaning they have the lowest repulsion. But look what happens with a lone pair. It's only pulled by one nucleus, so it just balloons out. It demands so much more spatial volume. Because of that, the repulsion between two lone pairs is the absolute maximum. This little inequality is literally the secret to everything we're going to discuss next. Now, to quickly figure out any molecule's shape for your exams, I really want you to use this reliable three-step algorithm. Step 1. Just draft the Lewis structure. Map out all your bonds and lone pairs. Step 2. Count your repulsion units. And please remember this golden rule, okay? Treat a double or triple bond as just one single repulsive unit, because those electrons are all locked together in the exact same general space between the two atoms. And step 3. Simply use that count to determine your final shape.
All right, moving to section 2, standard electron pair geometries, the perfect shapes. Take a good look at this base geometry matrix. If you have two repulsive units, like we see in carbon dioxide, they push 180 degrees apart, giving us this beautifully perfect linear shape. If you have 3 units, like in boron trifluoride, well, they spread out completely flat on a plane at 120 degrees, so that's trigonal planar. And if you have 4 units, like in methane, they push out into 3 dimensions, forming a tetrahedral shape, with bond angles of exactly 109.5 degrees. My dear students, you absolutely must memorize these specific bond angles for your MCQs. They come up all the time.
Okay, let's bump it up to the advanced geometry matrix for those molecules that like to break the octet rule. For 5 units, like phosphorus pentachloride, we get a trigonal bipyramidal shape. Notice how it actually has 3 coplanar bonds right around the equator, and then 2 perpendicular bonds sticking straight up and down. And for 6 units, like sulfur hexafluoride, we get this really neat octahedral structure, where every single angle is a perfect 90 degrees.
Section 3, the impact of lone pairs, or as I say, the plot twist.
So this really brilliantly illustrates the totally invisible impact of lone pairs. Let's compare methane, ammonia, and water. All 3 actually have 4 repulsive units, so they all start with that exact same perfect tetrahedral framework of 109.5 degrees. But ammonia has 1 invisible lone pair just pushing down from the top. And since it demands greater volume, it squeezes the 3 visible hydrogen atoms closer together, completely degrading the angle and forming a trigonal pyramidal shape. And water is even more extreme. It has 2 invisible lone pairs pushing down. They squeeze the bonding pairs even tighter together, leaving us with this bent or angular shape. Now, this brings us to a seriously crucial point, one that tricks students in past papers every single year. You simply have to know the difference between geometry and shape. Electron pair geometry is the total arrangement of the repulsive units. It includes those invisible lone pairs. But molecular shape only describes the visible atomic skeleton, just where the actual atoms are sitting. So for water, the geometry is tetrahedral, but the shape is angular. Keep that crystal clear in your mind, okay? On to section 4, hybridization and bond anatomy, the microscopic mechanics.
So here is the huge problem that actually led scientists to the theory of hybridization. Look at the ground state of carbon. It only has 2 unpaired electrons in its 2p orbitals. Logically, it should only be able to form 2 bonds, right? But we all know methane has 4 identical bonds. So how does that work? Well, the atom actually absorbs a little bit of energy to promote an electron from the 2s up to the empty 2p orbital. Then, in this kind of imaginary mathematical mixing process, it blends that 1s orbital and the 3p orbitals all together. The result? 4 perfectly identical sp3 hybrid orbitals, totally ready to form symmetric bonds. This orbital mixing matrix shows that logic just beautifully. If you mix 1s and 3p orbitals, you get sp3 hybridization, leaving 0 unhybridized p orbitals, and that results in our tetrahedral geometry. If you only mix 1s and 2p orbitals, you get sp2 hybridization. That leaves 1 raw p orbital completely untouched, giving us a trigonal planar geometry. And if you mix just 1s and 1p, you get sp hybridization, leaving 2 unhybridized p orbitals, which naturally gives us a linear geometry. Now you might be wondering, what actually happens to those unhybridized p orbitals? Well, that brings us to the anatomy of a bond. When orbitals overlap head-on, right along the central axis between 2 nuclei, they form a super strong sigma bond. That's your primary molecular skeleton. But those leftover, unhybridized p orbitals sticking up parallel to each other, they overlap laterally, sideways, to form a pi bond. Remember this golden rule. A single bond is always 1 sigma. A double bond is 1 sigma and 1 pi. And a triple bond is 1 sigma and 2 pi bonds. Oh, and those pi bonds, they are exactly what lock the molecule in place and prevent it from rotating.
Moving to Section 5, Resonance and Formal Charge, Evaluating Stability.
First things first, let's debunk a very common misconception. I call it the myth of the flipping bond. When you draw resonance structures for something like the nitrate ion, it honestly looks like a double bond is just constantly flipping back and forth between the oxygen atoms in real time. But that is absolutely not true. The reality is the structure you see at the bottom. Those contributing Lewis structures, they're totally imaginary. The true molecule is a single, permanent resonance hybrid, featuring this beautiful delocalized pi electron cloud that spreads out smoothly over the whole molecule, making it incredibly stable.
But sometimes you'll find one resonance structure is actually more stable than another. To evaluate competing structures, you absolutely must use this exact ranked checklist from your syllabus. Number 1, always try to satisfy the octet rule first. Number 2, minimize formal charge separation. Basically, getting everyone as close to 0 as possible is the goal. Number 3, never put similar charges right next to each other. And number 4, if you absolutely must have a negative formal charge, make sure it sits on the most electronegative atom. If you just follow this checklist in exact order, you will always identify the most stable structure. Guaranteed.
And our final section, number 6, Polarity and Electronegativity, the Chemical Behavior.
Look at these 2 examples of polarity and dipole moments. Up top, we have hydrogen chloride. Now, chlorine is highly electronegative, right? It's actively pulling the electrons towards itself. This unequal pull creates a permanent dipole moment, a little delta negative end and a delta positive end. It is a highly asymmetric, polar molecule. But then look below at carbon dioxide. It absolutely has polar bonds, but because VSEPR theory dictates perfectly linear, symmetrical geometry, those pull vectors exactly cancel each other out in opposite directions. The result? A completely nonpolar molecule. It just goes to show shape really does matter. And as a final, really powerful takeaway for today, please remember that an atom's electronegativity, its pulling power, is not just some static number you read off the periodic table. It dynamically adapts based on 4 key drivers. Number 1, hybridization. The more s character an orbital has, the closer the electrons are to the nucleus, so sp hybridized atoms pull harder than sp3. Number 2, ionic charge. Positive ions simply pull harder on electrons. Number 3, oxidation state. A higher oxidation number means a much stronger pull. And number 4, neighboring atoms. If a central atom is surrounded by highly electronegative neighbors, its own pull gets a massive boost. And wow, that brings us to the end of our masterclass on structure and bonding. We have built our way all the way up from basic VSEPR theory to advanced polarity. Thank you so much for learning with Study Hub Sri Lanka today. I really hope this explainer made the syllabus so much clearer for you.
We will meet with another episode of your science subject very soon. Until then, please do make sure to subscribe to the channel and click that little bell icon so you receive instant notifications about all our upcoming study tips explainers. But before you go, just think about this for a second. If just one single invisible lone pair can change the shape of water and literally make all life on Earth possible, how might manipulating these microscopic shapes unlock the next great medical or technological breakthrough? Keep studying hard, my dear students, and I will see you next time.